This is Mr. Precella, continuing to work on a review sheet for the second test in my face-to-face trigonometry class. Again, this is my face-to-face, not my online trigonometry class. And we've gotten down through problem 11 in the first part. So I'm going to flip on over. Before I start actually working problems, I was writing identities that you need to know, and in the first part I'd written the sum and difference identities. I'm going to now write the double angle identities, and the double angle identities can be derived easily from the sum and difference identities just by thinking of 2a as a plus a. So if we think of it as a plus a, then you're going to have sine a cosine a plus cosine a sine a. That would just be 2 sine a cosine a. Now for the cosine double angle identity, there's actually 3 of them. The first one you get by doing what I just did with the sine double angle. Thinking of 2a as a plus a, so it'd be a minus a. Cosine a cosine a, so it would be cosine squared a minus sine squared a. Then the other 2 forms of that same identity involve using the first Pythagorean identity, write everything in terms of sine squared, or then write everything in terms of cosine squared. If I replace the cosine squared with a with 1 minus sine squared a, I have 1 minus sine squared a minus sine squared a. So 1 minus 2 sine squared a. Or I could rewrite everything in terms of cosine by replacing this sine squared a with 1 minus cosine squared a, and you get 2 cosine squared a minus 1. And we derived all of those in class. Finally, the double angle identity for tangent 2a, I think I'll write it right here. Tangent 2a. One just comes straight from thinking of 2a as a plus a, so it's tangent a plus tangent a, 2 tangent a, over 1 minus tangent a times tangent a is tangent squared a. Those identities might pop up on some, or will pop up on some of these problems we're going to be doing today. So let's see, let's look at problem number 12. Y'all see that? 2 cotangent x all over 1 plus cotangent squared x. Well, that 1 plus cotangent squared x sure reminds me of that Pythagorean identity. 1 plus cotangent squared x equals cosecant squared x. So it's just so tempting to go ahead and replace it with the bottom with cosecant squared x. That's what I think I'm going to do. Seems logical. I've mentioned when you're simplifying these identities or verifying trig identities, you've got to start somewhere. You can't just look at it. So 1 plus cotangent squared x is cosecant squared x. Then what else could we do? If in doubt, what can you do? Write everything in terms of sine and cosine. So that's what I'll try to do. I'm going to think of this 2 cotangent x is 2 cosine x over sine x all over, so trying to keep this black line as that black line. Cosecant squared x would be 1 over sine squared x. So, oh wow, that's a complex fraction or compound fraction, whatever you want to call it. We could simplify it by getting just a 1 below the black line by multiplying above and below by that pink sine squared x. What would happen if I multiply above and below by sine squared x? Well, the sine squared down there cancel, and up above the black line I can cancel this sine x with one of these. So really all I'm left with, let me just write down using the correct colors what I'm left with. I have the purple 2 cosine x and the pink just sine x. And look at our answer choices. It's a double angle. Which one is it? 2 cosine x sine x. Did y'all hear that? 2 cosine x sine x is sine 2x. It's the double angle identity for sine. I wrote it with the sine first, but sine x times cosine x, same thing as cosine x times sine x. So that is which one? B. Now, number 13. Let's see. Sine x plus cosine x all squared. Well, sine x plus cosine x all squared. Well, to expand a binomial, binomial has 2 terms, and well, this is 2 terms, I guess it's not really a binomial, but okay, sine x plus cosine x has 2 terms, so to square it, you're going to FOIL it out. Some of you can do it in your head. I'll write it out just to try to show my thought process, but yeah, I know y'all can do it in your head, and so can I. Sine x times sine x is sine squared x. Let's do the outer and inner all in one step. Sine x cosine x plus cosine x sine x. Those would just be 2 sine x cosine x. And what's the last one going to be? Cosine x times cosine x. Is that a cosine squared x? Oh wow, this is an easy one, isn't it? You'll see how this is going to fall out so nicely. The sine squared x plus cosine squared x I can replace with a 1. And so since 3 of the answer choices had a 1 to get started with, I feel pretty confident. And what about this? Oh, what just fell? This 2 sine x cosine x, is that the double angle identity for sine again? The one we just finished using? Sine 2x, 2 sine x cosine x. So 1 plus sine 2x, that is C. Any questions? What about number 4? Ooh, now number 4 takes a little thought. If you look at it, there are 2 double angles in there. Sine 2, number 14, I mean. Number 14 is going to take a little thought. There are 2 double angles in there. Sine 2x and cosine 2x. The cosine 2x, that when you're working with the double angle for cosine, that's the one that takes the most thought because there's 3 of them. And it's always, you know, ooh, which one's the best one to use? Which one will make it fall out the best? And this is a good example of that. Now for sine double angle or tangent double angle, there's not 2 of them. Now there's no doubt about for, let me color code this. Number 14. Sine 2x all over 1 minus cosine 2x. Okay. Let's see. Well, for the sine 2x, this is not any other possibilities. I'm going to replace it with 2 sine x cosine x. And then we have a 1 minus. Now here's where it's going to take some thought. Look at how it's going to simplify. It's going to simplify either to sine squared x, cosine squared x. Tangent x would just be sine x over cosine x. Or cotangent x would be cosine x over sine x. So if it's going to simplify that much, somehow or another, this 1, we put this right there, that 1, it needs to be gone. So here's where it's going to take some thought. If I'm going to replace cosine 2x with one of these double angle identities, which one should I replace it with that'll get this 1 to subtract out? Like, I wouldn't use this one. Can you imagine if I put cosine squared x minus sine squared x there? That'd really be a mess. I'm thinking it's this one right here. If I replace cosine 2x with 1 minus 2 sine squared x, replacing cosine 2x with 1 minus 2 sine squared x. But be careful. This black minus goes to all of that. I put parentheses around there. Is that sort of hinting what we're going to need to do with that black minus? Let's see. Up on top, we have the pink 2 sine x cosine x. And on the bottom, we have the black 1. Now, if I distribute this minus, that would give me a minus 1 and a plus 2 sine squared x. So look how nicely this is going to simplify now. On the top, we have 2 sine x cosine x. And on the bottom, 1 minus 1, that would be 0. So just 2 sine squared x. Oh, this simplifies nice, doesn't it? Because now the 2's cancel, and I can cancel one of these sine x's. So the pink sine x I cancel with one of these black sine x's. So all that's left is just a cosine x on top, sine x on the bottom, which is cotangent x. Any questions there? Well, okay. Number 15. 2 sine x, no, sine 2x minus cotangent x. Let's see. Number 15. Sine 2x minus cotangent x. Well, what the heck can we do on this one? Well, 3 of the answer choices have a cosine 2x in it, so I wouldn't be surprised if a double angle, cosine double angle pops up somewhere along the way. To get started, I'll replace sine 2x with 2 sine x cosine x minus cotangent x is cosine x over sine x. And I sure mentioned this in my math face-to-face class. I've said it enough times. But this course is the big stepping stone in your mathematics knowledge, where you stop just the repetitive patterns and stuff. But if you're, I've said this to the students face-to-face, but if you're watching this, I'll say hi to everyone watching it in Japan. This will be the first time you will have heard me say this probably. With trigonometry, everything, the patterns just stop. Okay, and you've got to think your way through the stuff. So here, what I'm going to do, I think, is just get a common denominator. The common denominator would just be that green sine x. Huge denominator, sine x. Well, if I'm going to put a green sine x down here, let me lift this up so y'all can see it. If I'm going to multiply the bottom by sine x, I need to multiply the top, so there's going to be a square now. Sine x, cosine x times sine x. So there's two of these sine x's. So we have 2 sine squared x cosine x minus, now this second fraction here already has the green sine x as its denominator, so just cosine x. Well, what can we do? Well, we can just stare at it and stare at it. We've got to do something. So looking at the top, thinking, what can I do? We've already written it in terms of sine and cosine. Well, I notice that there's a cosine x in each one of these terms. What if I factor that cosine x out? So on top, what would happen if I factored this cosine x out? If I factored a cosine x out there, what would I have in the parentheses then? I would have the 2 sine squared x, and then the blue minus, and what am I going to have to put here in order to get that cosine x when I distribute? There'd still be a 1 all over sine x. I'm starting to feel better about this, because cosine x over sine x, that's cotangent x. And notice 3 of the answer choices have a cotangent x in there. Now, what about this 2 sine squared x minus 1? Well, that looks a lot like this second double angle identity for cosine. Cosine, let me write this down just on some scratch paper. So down here, just some scratch paper. So trying to show my thoughts. Cosine 2x is 1 minus 2 sine squared x. Well, what I have here is 2 sine squared x minus 1. So I would need this 1 to have a negative on it, and this 2 to be positive. So what I could do is just multiply straight through by a negative 1. Negative, negative, positive. Do I now have 2 sine squared x minus 1 equals a negative cosine 2x? Y'all see that scratch paper there? My thoughts. So I'm replacing all of this, that circled stuff, with cotangent x. I'm going to replace this time stuff with a negative cosine 2x, and I'm not going to leave it like that. Positive times negative, I'm just going to write it as negative cotangent x cosine 2x, which I believe is one of the answer choices. Negative cotangent x cosine 2x. Okay. Any questions? That's number 15, especially down here. There's a lot going on here in my thoughts. Another way we could have done this, instead of factoring out a positive cosine x, if we had factored out negative, then that would have given us a negative 2 sine squared x plus 1. That might would have been a, well, I don't know. You sort of, if you're doing it that way, then you know how it's working out anyway. Any questions there? I need some more paper. What's number 16? Complete this identity. Okay, so number 16. Cosine theta over 1 minus cosine theta. Then minus, trying to put the colors here, and also spreading it out. Cosine theta over 1 plus cosine theta. Well, what can we do here? Well, we have two fractions with different denominators. So what I would think to do is maybe add those two fractions together. If we're going to add them together, we've got to get a common denominator. And what would that common denominator be? Well, common denominator would just be the black 1 minus cosine theta times the, what color is that? Pink 1 plus cosine theta. So you begin to see why I left all this room. Here, there's already a black 1 minus cosine theta. So to get a pink 1 plus cosine theta here, we're multiplying above and below. Now here we already have the pink 1 plus cosine theta. We need a black 1 minus cosine theta there. So let's see. Right here, go ahead and distribute that. You'd have a cosine theta plus cosine theta times cosine theta. That'd be cosine square theta. Now when you distribute on the next one, be very careful. You also, this minus sign is actually right up here. You need to distribute the negative cosine theta. If you'd written it all, it's just one big fraction before distributing, which is how I recall doing it when I did a problem like this in class, when it was a homework. You have a minus cosine theta, and then what? A plus negative cosine theta times negative cosine theta. That's a positive cosine square theta. Start simplifying. The cosine theta minus cosine theta, that subtracts out. And we have cosine square theta plus cosine square theta. That would be a 2 cosine square theta. And what about the bottom? Well, let's FOIL this out. What would we have? We'd have a 1. Now the outer and inner are subtracting out, right? We'd have a 1 cosine theta minus 1 cosine theta. So just a 1 minus cosine square theta. Hopefully at this stage you recognize that. That's why you were supposed to memorize these identities so long ago. On top we have a 2 cosine square theta, and using a Pythagorean identity, 1 minus cosine square theta, 1 minus cosine square theta is going to give you a sine square theta. So let's see, how could we write that? Just 2 cotangent square theta. Let's see, that would be B. Any questions over that? Number 17. Well, can't be much doubt where to start on this one. Okay, it says cosine theta plus 270 degrees. Now, let's see, how do I expand that? What was that pattern? This is a sum for cosine. It's cosine, cosine, change, sine, sine. Now I'm going to think of the unit circle. 270 degrees. That would be right here. And what's that point of intersection? It would be 0, -1. Remember, on the unit circle, the x-coordinates are cosine, the y-coordinates are sine. It's in alphabetical order. So the cosine of 270 degrees is 0. So cosine theta, or anything times 0, is 0. Minus sine theta times sine 270 degrees. The sine of 270 degrees is a -1. Negative sine theta times -1, that's going to be a positive sine theta. See, all of that is 0 over here. So just a positive sine theta C. Well, they can't all be that easy. Let me see. What is next? Okay, just complete the identity. It doesn't give us a lot to go on. It's number 18. Cosecant x times sine x plus cosine x. Well, if in doubt, hopefully at this point you've got the hang of it. When in doubt, write it in terms of sine and cosine. There were no double angles or anything there. Oh, this one's going to work out nice, isn't it? If I distribute this 1 over sine x, sine x times 1 over sine x would just be a 1. Sine x, excuse me, 1 over sine x times cosine x would be a cosine x over sine x, which would just give us a pink 1 plus what? Cotangent x? That's right. 1 plus cotangent x d. A few more of these remaining. Let's see, number 19. Oh, sine squared x plus sine squared x times cotangent. 19. Sine squared x plus, I'm color coding it so you can keep up with sine squared x. Oh, this one, can you do it in your head? Well, with all those squares and stuff, I wouldn't be surprised if a Pythagorean identity comes in. Oh, pardon me. You could factor out the sine squared x, but what I just, as I was writing it down, what my brain processed was, oh, let's write it in terms of sine and cosine. Really, that's the only thing that you can write in terms of sine and cosine is the cotangent. Just write it as cosine squared x over sine squared x. You see what I'm saying? When you're multiplying fractions, you can cross cancel. So all that's left is sine squared x plus cosine squared x, which is a 1. Okay. Now, I've warned you, when these problems regenerate, sometimes students start, oh, well, if I see a problem that looks like like this, I'm going to expect the answer to look just like that. Well, you know, the signs S-I-G-N-S frequently change, okay? So don't just rely on these too much, but the logic is the same. If you see a problem that looks sort of like this, I would think, okay, I want to somehow replace the cosine 2x with one of those things to get the 1 to subtract out. Now, oh, I don't need another sheet of paper. I have room to do the last one, number 20, right here. Tangent x minus pi. Well, that's a sum formula for tangent. That's tangent x. Let's see, tangent is sine over cosine. So same over change. 1 plus tangent x tangent pi. Had I written those identities? Have I thrown it away? Yesterday, when I did part 1 on the video, on part 1 of the video. Right here, that's what the S over C, same sign over change. The way I remember same over change is tangent is sine over cosine. Okay. Now let's see, tangent pi. Well, let's think of the unit circle. On the unit circle at pi would be right there, 180 degrees. The point of intersection is -1, 0. Oh, this is going to work out easily, isn't it? Tangent pi would be sine over cosine. So I'm going to replace those tangent pi's with 0 and 0. So on top, we just have tangent x minus 0, so tangent x. On the bottom, we have 1 plus tangent x times tangent pi. Tangent x times 0 is 0. So it's just going to be tangent x. Hey. Any questions on that? Well, this is the review for the face-to-face college algebra, trigonometry class, their second test. This is the big test over identities. There's just no way around having these basic identities memorized. Pythagorean, quotient, reciprocal, negative angle identities, sum and difference, and double angle identities. Okay? So I'll see you in class. And if you're watching in Japan, sayonara. Thanks a lot. Bye-bye.